This is problem 2 from the final exam for 2020, and it comes from, I think, maybe a IB paper from 2018. Paper 2 problem is we're asked to find, first of all, the time taken for this battery to discharge. So this is the question. Here is the setup. A girl rides a bicycle that is powered by an electric motor. A battery transfers energy to the electric motor. The EMF of the battery is 24 volts. It can deliver a charge of 45 kilocoulombs when completely discharged. She can go at a maximum speed of 6 meters per second just from the battery, and the maximum distance she can go is 25 kilometers. How long does it take for the battery to discharge? Okay, so we're looking for the amount of time. This problem, I think, can be a little tricky because you've got all this information, and it's actually a very simple question. If I ask you how long it will take you to travel 25 kilometers if you're going 6 meters per second, you should be able to find the time very simply by dividing the distance by the rate. So that's a very basic problem, but it can be easy to overlook how easy that is because of all the information, and it's an IB test. So that's just going to be the distance traveled. So this is number 2 from the exam. It's 25 kilometers, so that's 25 times 10 to the third meters divided by 6 meters per second. And that should come out to be 4,166.6 repeating seconds. Everywhere we're given 2 sig figs, and so our answer should be 4,200 seconds. Okay. And for B, what we want to know is the average power output of the battery. Okay, so power, we know, is going to be work divided by time. So this time that I used here is going to be useful. Now I need to find out how much work I'm going to be able to do, though. So again, I've got quite a bit of information here. I got information on electricity. I've got electrical information up here. And then I've also got down here more mechanical information. So which is it going to be? What do I use here? I use this information here to find out how long I can run this bicycle with this battery. How much work am I going to do, though? Can I figure out the work from this information here? Well, I don't really know any forces that are acting, so it might be difficult to find how much work I'm doing here. But here I can find out how much work I'm doing, because remember, the definition of a volt is the work per coulomb, how much work each coulomb of charge can do. So how much work am I going to do? The battery is going to do the amount of work equal to the product of 24 volts times 45 kilocoulombs, because remember, a volt is the joules per coulomb, how much work each coulomb of charge can do. So the answer there is going to be the work that I do. So the power is going to be equal to work over time, but the work is going to be equal to the charge times the potential difference of each charge, and that'll be divided by time. So what I get here is I have 45 kilocoulombs, okay, times 24 volts. And this is over the answer that I got here. Now, I prefer that we keep this is a 24, keep this to the unrounded figure and then round at the end. So remember here, what do we put in? Do we put in the 4,200 or do we put in what we have here? If this is still in your calculator register, I suggest that you just recall it and do the calculation that way. What we should get is in the neighborhood of, now I actually used in my calculation, though, I went and used 4,200. But if it's in your calculator register, you might as well use the exact answer and then round at the end. This should all come out to be about 257.1 watts. And then to the proper number of significant figures, that would be 260 watts. Back to 2 sig figs. Okay, part C. Part C says the bicycle has a meter on it and it displays the current and the terminal potential difference. The terminal potential difference, not the EMF. For the battery, when the motor is running, so the diagram here, we have a picture that shows the meter reading at some point. And again, we're reminded that the EMF of the cell is 24 volts. Okay, so here we have a difference between the potential difference measured at the terminals, what we actually measure, and then the electromotive force, or like the rating, if you will, of the battery. So this equation comes from section 5 in the manual, and what you should find there is that the EMF is equal to the terminal potential difference plus the potential difference caused by the internal resistance. So this is going to be the current, and then this is going to be the internal resistance here, this little r. Okay, and we could rewrite this. We don't really need to right now, but we could rewrite this as I times the resistance within the circuit plus the resistance within the cell. And remember, we consider those to be in a series, so we can just add them. At any rate, I have everything I need because I'm told that the EMF is 24. I've got the reading on my meter of 18, and then that's plus IR, and then the reading on the ammeter is 6. So I just solved this simple linear equation here, and I get 6 is equal to 6R. So R is equal to 1 ohm. All right, that was 2C. For part D now we are asked to determine the battery is made of an arrangement of 10 identical cells, as shown here. Calculate the EMF for one cell, okay, and then the internal resistance for one cell. So the way these are arranged is they're arranged into 5 pairs. Each cell, each battery, if you like, is we have 5 batteries in series, and each of these is a battery, a collection of cells that has 2 in parallel. Okay, so if these 5, 1, 2, 3, 4, 5 here, if these 5 have a total voltage or a total potential difference of 24 volts, then each one of these is going to have 24 divided by 5, or 4.8. So since we have 5 cells, 5 batteries in series, and each one of those is made of 2 cells in parallel. If they're in parallel, then that means by definition that they have the same voltage across them. So all I have to do is say that I've got 5 cells, and together each one is going to be 1/5 of the 24. So that means that each one of the cells, each one of the batteries, the pair of cells, has a potential difference of 4.8 volts. But they consist of 2 cells in parallel. And so each cell also has a potential difference of 4.8 volts because they're connected in parallel, and so they have the same potential difference as the configuration does. Okay, I hope that makes sense. And then finally, we want to find part E, asks for the internal resistance. Well, going back to the way the way this thing is configured, we know that from part C, we determine that the total internal resistance of this battery right here is 1 ohm. Again, it consists of 5 smaller batteries of 2 cells each in series. So by the definition of series, I can say that each one of these smaller batteries of 2 cells is going to have 1/5 of an ohm. Okay, because if I add them together, I get a total of 1 ohm, and they're in series. But now, looking back into each of these batteries has 2 cells in it, and I want to know the internal resistance of one cell. What that means then is that each of the smaller batteries consisting of 2 cells has to be equal to 1/5 of an ohm. but now they're in parallel. So remember how that goes. For parallel, I have to say that when I have the resistance, it's going to be the reciprocals of the resistance. So if little r here, I have to add the reciprocals and then take the reciprocal of that sum. And that needs to be equal to, well, 1/5, because these now, 5 of these in series equals 1. Okay, so I have to solve this equation. So that means that 1 over r plus 1 over r is equal to 5. I take the reciprocal of both sides. So that means 2 over r equals 5. 5r equals 2. R is equal to 2/5 or 0.4 ohms. Okay, and that's that.